So I was talking about diamonds just a little bit ago, and let's see. So the fact that it has such a high index of refraction means that when light encounters a diamond, it'll take longer to bounce around in the diamond, and basically that gives the diamond what's called a luster. There are some materials called Bose-Einstein condensates where we can actually reduce even more nowadays. This is an older slide, but we can reduce the speed of light by increasing the index of refraction so much that it'll slow down the speed of light to walking speed. Alright, so, oops, we had our equation. Where is that? Sorry. Oh, there it is. All right, so let's do an example with this. It's a very simple equation. C is always 3 times 10 to the 8th meters per second. The velocity is the velocity in the medium, as I was saying. All right, so let's do a quick example of that. And let's see. Let me get my pen here. All right, so let's do an example. Remember, this is what we're using. N is equal to C over V. And so, for example, let's say that the index of refraction N was 1.4. I'm just going to make that up. See, that's a unitless number. And so what we want to know is what's the velocity in that medium. Okay, so the medium is defined by the index of refraction of 1.4. So what's the velocity in that medium? That's what we're going to answer. And of course, we're going to use this equation to solve that. Of course, the speed of light is 3 times 10 to the 8th. If you do some algebra on this, basically the N and the V exchange places, and so I'm just going to, you can do the algebra. So it's just C over N. And so you can plug the numbers in here. So this is always 3 times 10 to the 8th meters per second. That's 8th meters per second. And then you just divide by 1.4. Alright, and let's see. Let me get my calculator real quick. 3 times 10 to the 8th divided by 1.4. So, you know, I get this really large number. I'm going to change it to scientific notation. So it's like 214 blah blah blah. Let's see. So I'm going to do 2.14, and that should be times 10 to the 8th. Let me count the zeros. 1, 2, 3, or the decimal places. 1, 2, 3, 1, 2, 3, 1, 2. Yeah, so it's 2.14 times 10 to the 8th meters per second. Alright, that's to the 8th. Alright, so, I mean, that's kind of how you do this. Here, let's do another quick example. It's fairly, like I said, these are fairly simple. So, you know, if you don't know, let's say you know this time you know the velocity in the material. So suppose the velocity is, I don't know, how about 1.5 times 10 to the 8th meters per second. Alright, and so we want to know what the index of refraction is. So the speed of light is measured in that particular material to be 1.5 times 10 to the 8th, and so what's the index of refraction? And so the index of refraction is the speed of light, so it's 3 times 10 to the 8th meters per second divided by, in our case, this 1.5. So 1.5 times 10 to the 8th meters per second. Notice the meters per second cancel and gives us a unitless number, as it should. And so when you do this, it's really just 3 divided by 1.5 because the times 10 to the 8th cancel. So the index of refraction of that particular substance or medium, if the light is traveling through there, is 2. Alright, so pretty simple. Alright, so we're going to continue here. So the next thing is this idea, here let me expand this slide a little bit, is of course, I already mentioned the fact white light is composed of all the colors of the rainbow. Isaac Newton actually proved that by using white light and two different prisms. All right, so let's see. Whoops, let me go back one. Here's something interesting about rainbows. A rainbow, you have to have the situation exactly right. So a person has to be like standing over here. The sunlight is generally behind that person, and then the rain is in front of them. So if they turn towards the rain, what's happening is the light is dispersed, and just like in a prism. So what's happening is the red light gets bent the least, and the blue light gets bent the most, because the blue light has a greater a smaller wavelength, and so it gets bent the most. And and then in between are all the colors of the rainbow that we would normally see, and so that gets passed on to the viewer somewhere over here, and so they see all the colors of the rainbow from blue to red. And sometimes you'll actually see a double rainbow, and so in that particular case you get another reflection. So this light right here would bounce one more time and then spread. You would be able to see it spread again. It's pretty rare to see that, but anyhow. This is our equation. The speed of light is equal to the wavelength times the frequency. If you remember the stuff from Chapter Challenge where we studied Chapter 5 about waves, this is just a equation, but it's for light. So it's not just any speed, it's the speed of light is equal to the wavelength in meters times the frequency in hertz. So let's do some examples with that. Here, let me see what the next thing is. Oh yeah, let's do some. So here we go. I'm just going to rewrite this equation. The speed of light is lambda, the wavelength times the frequency. So lambda is called the wavelength. It's measured in meters, and the frequency is measured in units called hertz, which are just 1/seconds. And of course, the speed of light is always what it is in a vacuum, is 3 times 10 to the 8th meters per second. All right, so if you know what the wavelength is, you can always figure out the frequency, and conversely, if you know the frequency, you can always figure out the wavelength. Let's do a couple of examples. Suppose you had a frequency, and this is if you have like a radio on the FM dial. Let's say you had a radio station at 96.1 megahertz. All right, and we want to know, let's say we want to know the wavelength. So we want to know lambda of that particular radio station. So notice the frequency should be in hertz, not megahertz, so we can easily change that if we remember our metric prefixes. So this would be 96.1. By the way, on the FM dial, it's in megahertz. On the AM dial, it's in kilohertz. So just to let you know. So that's a mega is times 10 to the 6th hertz. And so if we go back to the original equation, we have to solve this for lambda. And so I'm just going to divide both sides by f. I guess I could do that right here. So divide both sides by f. The f's cancel on that side. And so lambda, here, let's write that. Lambda equals, that's not a good looking lambda, all right, is equal to the speed of light, so it's 3 times 10 to the 8th meters per second, divided by the 96.1 times 10 to the 6th, right, because it's megahertz. And of course it's hertz, and hertz is really 1/second, so this 1/seconds cancels hertz, giving us an answer in meters. All right, so let me do this in my calculator. All right, so the answer I get when I do this in my calculator is about 3.12 meters. That's supposed to be an M right there. Okay, so here I'm going to rewrite it just to make it look a little bit better. So lambda is equal to 3.12 meters. Okay, so that's the physical size of the carrier wave for this particular radio station. If there happened to be a radio station at 96.1 megahertz, or they just call it on the radio, they would just call it 96.1, and so that's the physical size of the wave. By the way, let me just here's a little quick engineering. The receiver in your car or wherever you happen to be picking up this radio station, what it does is it has to change the antenna to roughly this size. It's not exactly that, but to this size to be able to pick up that radio station and not pick up any others. Now, in a car, you're not physically changing the size of the antenna. What it does is it electronically does that with devices called capacitors and inductors. So when you tune in this station, what you're doing is you're electronically changing the wavelength to be this size. It's actually 1/4 this size, but that's more of a technical issue. Anyhow, so there's our first problem. Let's set up another one. Yeah, we'll do that right here. So now let's say that we know the wavelength. All right. So let's say the wavelength is, I don't know. How about well, let's go with the wavelength of red light, for example. Okay. So let's say this is the deepest red that humans can see. It's about 700 nanometers. So again, that's not in meters. That's in, you got to use your metric prefixes here. That's why it's so important to learn those. So 700 nano means times 10 to the minus 9th meters. All right, and so now we want, let's say we had red light. We want to know the frequency of this red light. Okay, so what's F? And F, of course, similarly is the speed of light divided by the wavelength, right? So let's put those numbers in. So this is 3 times 10 to the 8th. Remember, it's always that, meters per second. This time we're dividing by 700 times 10 to the minus 9th. That's 9. It's supposed to be a 9. And that's meters. And of course the meters cancel. And so it leaves you with a 1/seconds, which of course is hertz, right? That's exactly what we mean by hertz. So let me quickly do this on my calculator. Divided by 700, shift EE to the minus 9th. All right, and so the frequency that I get is about 4.28. They kind of there. So I'm going to round. I'm going to round it to 4.3. Okay, and it's times 10 to the 14th hertz. All right, and so that's the wavelength of the deepest red the human eye can see. Okay, so the 700 nanometers. Just to let you know, also, so visible light goes from. I know it showed you this before, but I want to do it in wavelength. So lambda. So that's lambda red up here, and lambda blue, or the deepest blue that the human eye can see. Some people call that violet. Is 400 nanometers. 400 nanometers. So if you're ever asked a question, is a particular form of electromagnetic radiation in the visible, it's got to be between 400 and 700 nanometers. Okay, so this of course is lambda red. All right, so